Hi, I'm going to review chapter 12 stuff with you. So we're going to talk about exponents and logs, which are two things that are inverses of each other. So let's start off right away with an interest problem. So John is investing $5,000 into a savings account that either earns 4% interest compounded quarterly or 2.5% interest compounded monthly. So hopefully you remember, generally the more we compound something, the more interest is accruing over time, which just means that you're earning more interest. So notice the one that is 4%, quarterly means 4 times a year. The monthly one, it's a lower interest rate, but it's being compounded 12 times in a year. So we're going to figure out which account would be more wise for him to use. So I'm going to put a formula off to the side. So we're going to say A of t, the amount that he earns over a given amount of time, equals P, which stands for the principal amount, which is his initial amount, and then times 1 plus the interest rate over the number of times or the number of times that it's being compounded a year. And then the power up here, the exponent, will be nt, which is, again, the number of times that it's being compounded a year times the time. So what we're going to do then is substitute some values in. So I'll split this up, the one on the left side. I will do the 4% over here first. So I'll just fill in the values. P equals 5,000. R, the interest rate, is going to be 0.04 as a decimal. And then my n value is going to end up being, since it's compounded quarterly, n means 4 times during the year. And again, the t is going to be 10 years. So I have all the information. We'll just throw it right into a calculator basically. So what I'm going to do is calculate A of 10, so the amount after 10 years. So 5,000 times 1 plus 0.04 over 4, because it's r over n, and then that's going to be to the power of nt. So we're going to use 4 times 10 up here in the exponent, and then you can throw all that in the calculator too. So I'm going to do that, and if you do this correctly, it should come out to $7,444.32. So that's the first account with the 4% interest. Now we're going to look what happens if it's compounded monthly. So it'll be 12 times in a year, but it has a lower interest rate. So write down the same 4 pieces of information. The principal is $5,000. My interest rate this time is going to be 0.025. My n value is 12 because it's monthly, so 12 times in 1 year. And then it's over a span of 10 years. So I'm going to do the same exact thing. A of 10 equals 5,000 times 1 plus 0.025 over 12. And this will be raised to the power of 12 times 10. So then calculator, 5,000 times and this one came out to, hopefully I did this right, $6,418.46. So it seems right, even though the one on the right was compounded more, the fact is it has a 2.5% interest rate, and the other one has so much more of an interest rate at 4% that the compounding didn't really affect it too much as the actual interest rate did. So the account that I would recommend then would absolutely be the one that earned more money. So that would be the 4% compounded quarterly. Next one. So this will be a half-life problem. Good old Trevion has a 2,000 gram sample of an element with a half-life of 15 days. If he weighs the sample after 60 days, how much of it will remain? So we're going to use the half-life equation, which is going to be A of t equals A0, which A naught stands for his initial amount that he starts with. We're going to have a base number of 1/2 because it's half-life. And you're going to do this to the power of t over h. So you're going to take the amount of time divided by the actual half-life. And this amount right here is going to actually be the number of times that his half-life occurs, so the number of cycles of half-life. So the pieces of information that I need to fill in then, A0, his 2,000 gram sample. We need to know how long he's keeping it in for, and it is 60 days of the sample. The half-life, H, is 15 days, and that's given. So if you know that it's 60 days and each half-life is 15 days, that means the cycle is going to occur a total of 4 times. So you're really going to be taking half of 2,000 exactly 4 times. So I'll just throw the numbers into the formula. So we're going to do A of 60, because that's what T is, equals 2,000 times 1/2, and you can use 0.5 in the calculator, and it's 60 divided by 15. So throw in 2,000 in the calculator times 0.5 to the power of 4, and you get 125 grams. All right. Next one. Graph a function and its inverse on a coordinate plane, and then identify the following properties. So what I'm going to do first, realize I have a logarithmic function. I'm going to find the inverse of this, which would be f of x, or I should say f inverse of x, equals, and since 2.5 is your base number, it will be 2.5 to the x power. And what I'm going to do is kind of color code this, and I'll actually split this down the middle here. I'm going to call this xy, and this table is going to be for this inverse function. And what we're actually going to do is graph the inverse function first, the exponential function, and that's going to give me an idea of what that graph is going to look like. And then what I'll do is flip-flop the x and y coordinates, because an inverse function, again, it's a reflection over the line x equals y. So if you just flip-flop the x and y coordinates, I'll be able to plot this log function on the same graph. So the first thing I'll do is take 2.5 to the negative 1 power, and you can just leave these all as decimals. 2.5 to the 0 power is going to be 1. 2.5 to the first power is 2.5. And then 2.5 squared is going to end up being 6.25. So what I'm going to do with these values is plot them on the graph. Negative 1 is at 0.4, 0 at 1, 1 is at 2.5, and 2 is all the way up at 6.25. And this is going to be ugly and hideous, but I'm going to try to draw on this curve. Okay, that could have been a lot worse. All right, so that's my inverse function. So this is not the log function that we plotted. This is the inverse exponential function that we plotted first, so I'm going to label it as f inverse of x. And then what I'm going to do in order to graph my actual function is take the x and y values from before, and we're just going to flip-flop them. So the negative 1, 0, 1, and 2 are going to actually be my y values. The 0.4, the 1, the 2.5, and the 6.25 will now be my x values. And I'm going to plot these four. So I'll go over to 0.4 and down to negative 1, over 1, 0, 2.5, 1, and then 1, 2, 3, 4, 5, 6.25, and up to 2. So you can see that again, it is, oh my god, that was awful. It is going to be a reflection over the line y equals x. I'm going to draw that line in so that you can visually see where it looks like it's reflected. So this is the line y equals x. Basically, if you were to draw this on a piece of paper and just fold it over, you would see that the inverse really is just a reflection over that green line. So the one that's in red is my function f of x, and the one that's in blue is f inverse of x. So I'm going to list all the properties, and I'm going to do it for the function that's in red. So we're going to do it for just the function f of x. The domain of this. So we're talking about which x values are working here. Notice that there are no x values. The red does not cross on this side. It doesn't even touch the y-axis. So your domain is going to be x is greater than 0. Your range values. So notice this arrow is going to keep going down, 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 down. And this arrow over here, even though it doesn't look like it, it's going to keep going up, 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 up. So your range is all real numbers. Your x-intercept is this point right here where it crosses the x-axis at 1, 0. Now, since we said that it does not cross the y-axis, that means that we don't have a y-intercept. And the last part here, as far as this information is, since we had x equals 0, or x is greater than 0 was our domain values, notice I have an asymptote at x equals 0, which is the y-axis. So you have a vertical asymptote at x equals 0, and that's why you don't have a y-intercept. And if you look at the blue function then, you're basically flip-flopping all of these properties. If you think about it, your domain of the blue function is going to be all real numbers. Your range, instead of x equals 0, your range would be y is greater than 0. Your x-intercept, you wouldn't have one because the blue function doesn't cross the x-axis. And notice if you flip-flop the x and y coordinate, your y-intercept of the blue function is going to be 0, 1. And then lastly, your asymptote then would end up being at y equals 0 instead of x equals 0 because all your properties are flip-flopped. So the last little 2 bits at the bottom, as x approaches negative infinity, so again, we're looking at the red curve, basically as we move more and more to the left. So all of these points here, what's happening to the y value? So if you were to write out all the coordinates here, you'd see that your y's are getting smaller and smaller. So f of x is approaching negative infinity. And if you pick these points and you're moving more and more to the right, and again, if you wrote out every single one of those coordinates, you would notice your y values are increasing, which means that x is approaching positive infinity. So that's the entire process of graphing a function and its inverse. Just to quickly recap, we did start with graphing the inverse function first, which was an exponential function, and then I flip-flopped the x and y coordinates. Next ones. We're going to write an exponential function with these given characteristics. So this first one is decreasing on the interval of negative infinity to infinity. What that means is we're going to have some kind of decay, and it's going to be crossing through the point of negative 1, 4. So every exponential equation we're writing is in the form of y equals b to the x. So if you know that I have an x coordinate of negative 1 and a y coordinate of 4, I can substitute those pieces of information into this general equation, and the only thing that's really left to solve for is b. So what I'm going to do is substitute the 4 for y and the negative 1 for x, and I want to figure out what my base number is. So I'm going to bring this 4 down, and I'm going to simplify this right-hand side using one of my properties of exponents. If you have a negative exponent, you can rewrite this on the denominator as 1 over b to the positive first power. So then what I'm going to do is bring my b to the left side by multiplying, and then I'm going to divide. So I have a base number of 1/4. So the fact that it's decreasing on this interval and crossed through this point told me that it had to be a decay function, which means your base number would be between 0 and 1. So the fact that our base number is 1/4 is perfect. The last step is to really just write the equation. And so it's y equals 1/4 raised to the x power. And if it said write an actual function, I should be really picky about this. I'm going to write this as f of x so that it is in function notation. And I'll do the same thing for the next one too. So this next side, it says as x is approaching negative infinity, so as your x values move to the left, your y values, so f of x, is going to be getting closer and closer to 0. And as you move to the right when you read the graph, your x value, or your y values, f of x, are going to be approaching positive infinity. So that means as I'm moving left to right, we're going to be getting higher and higher, which means exponential growth. So we're going to be looking for a base number greater than 1, and it's passing through the point 3,8, which is somewhere over here. So I'll do the same exact process. I'm going to substitute 3 in for x and 8 in for y in that general formula that I was using, y equals b to the x. So if 8 equals b to the 3rd power, we need to figure out how I can get b. So since it's being cubed, what I'm going to do to both sides is take the cubed root. So on the left side, the cubed root of 8 is 2. And on the right side, it's going to cancel out, and you are left with b. So your base number is 2, which means at the very end, you're going to go in and write your function and say f of x equals 2 to the x power. And that is it for both of those. Next one is going to be a population problem. Suppose the population in the grand city of Gooteryville in the year 2010 was 625,000 and is decreasing at a rate of 1.1% every year. What will the population be in 2016? So I'm going to write down the population equation, which we are going to use, what's the variable? We can use a of t again for population, and we're going to use a naught times e to the rt. So population, after amount of time, you're going to take the initial population times e, which is kind of like how pi is. It's just an irrational number, to the power of our interest, or not your interest rate, to your rate of growth or decay, times the amount of time. So fill in some information here. A0 is your initial population, so we're talking about the 625,000. E is not a variable, it's going to be a constant, so I don't need to fill anything in. Now my rate, since we are decreasing at a rate of 1.1%, first of all, I'm going to slide my decimal 2 spots to the left and get 0.011. But since it's decreasing, I'm going to throw a negative sign out front of that. And then my population, be really careful for the time. It's in the year 2016. Notice we started in the year 2010. So just subtract those two numbers to figure out how much time has elapsed, and it would be a total of 6 years. So then all I'm going to do is throw those values into the equation. So A of t, so A of 6 equals 625,000 times e to the power of negative 0.011 times 6. And you can just throw that all in left to right, 625,000. E is the number that's right behind the natural log on your calculator, and it's e to the power of negative 0.011 times 6. And I'm getting a whopping 585,081 people. And I'm rounding down just because I end up with a decimal of 0.79. Even though that decimal is greater than 0.5, I'm rounding down because I'm talking about how many whole people are actually in this city. And there's not enough whole people to round up to 82, so I just round down to 81. And then the last ones that I have on here, converting between exponential form and logarithmic form. So the first two are in exponential form, so we will be writing these in log form. Or actually, I should say this first one is in exponential, and looks like the last one is too. So I'm going to write this in logarithmic form. Realize that 3 is your base number, 4 is the exponent, so I'm going to write it as log base 3, and you put the 81 here. So it's log base 3 of 81 is 4. So your exponent ends up on the right-hand side of the equal sign isolated, and your base number still stays the same. So the 81 just goes in this spot. So that's, again, just going from a basic exponent to log form. I'm going to do the same thing. Actually, I'll wait on that one. I'll do the next one. This one is in log form. I'm going to write this in exponential form, but I'm going to use a little trick to this, which is an inverse operation. So hopefully you know that natural log and e are inverses of each other. So I'm going to take e on both sides and raise it so that it's e to the natural log 4 is the power equals e to the y. So a little trick is you're able to cancel these out because these are inverses of each other. So those eliminate, and you're left with 4 equals e to the y. So that one would be a conversion from logarithmic form into exponential form, which is backwards of what we're going to actually be doing down here where my cursor is. The next one, very similar to what we did for the first one, except we're going to kind of go backwards from what's in blue. I'm going to keep 3 as my base number. Negative 2 becomes my exponent. And you set it equal to the 1 over 9. Again, nothing really tricky there. It's just backwards of exactly what's in blue. My exponent's on the right-hand side of the equal sign, so it becomes my exponent spot when I write it in exponential form. So same exact process. And same thing here as well too. When we know that natural log and e are inverses of each other, so if I want to get rid of this e here and write this in logarithmic form, you're just going to throw an ln on the left and throw an ln on the right. Realize that those will cancel out, so you're left with x on the left side, and on the right hand side you have natural log of p. And that is it. So again, the big concept from that last part is that exponential form and logarithmic form are inverses of each other, and e and the natural log are also inverses of each other.